Our project is CLEAR, sponsored by VoltServer, which stands for Colored LED Enhanced Automated Reader. Our technical directors are Camilo Giraldo and Nate Roth, with assistance from Consulting Technical Director Mike Smith. Our team comprises of 2 electrical engineering majors, myself and Nicholas Hatzies, and 2 computer engineers, Toby Awoleye and John Mendez. VoltServer is based in East Greenwich, Rhode Island, and they are most known for developing and delivering digital electricity, which is a safe and innovative power distribution platform. The goal of our project is to create a TX550 mountable sensor system that can view, analyze, and decipher RGB status LEDs and blink sequences incorporated in VoltServer's products. This will eliminate the need for a technician to tediously manually decipher them. Being able to redistribute that technician's manpower would save VoltServer time and money by automating the process. Given how commonplace LEDs are used to convey diagnostic info, this could eventually optimize end-of-line testing and quality assurance in a multitude of products. Meeting our ABO would mean delivering a working, enclosed prototype, including the mounting hardware for the TX550. This would include providing all required circuit, code, and assembly files, along with a complete bill of materials and a user manual. This is the list of team technical accomplishments achieved on this project thus far, which will be discussed in more detail during this presentation. This is the block diagram of how the overall product will function. I will mostly be talking about the LED sensors and sensing array. This is a list of my key technical contributions for the semester, with the PCB developmental work being shared by Nicholas Hatzies and myself, and the data collection being shared amongst all team members. For the light sensing aspect of this prototype, I designed a 2x3 grid array consisting of 3 sensors, one specializing in each color that needs to be sensed. The photocurrent generated by the LEDs will be calculated by measuring the voltage over a load resistor on each sensor and applying Ohm's law. The sensors we will be using in the array are a combo of NPN phototransistors in common collector active mode configuration and reverse biased PIN photodiodes. Over a dozen different sensors at varying wavelengths have been tested throughout the semester under both dark and ambient conditions across varying distances of 1 inch, 1.5 inch, and 2 inches between the LEDs and the sensor. Of that data collection, these Genacom company photodiodes and Vishay semiconductor phototransistors are the best options thus far for blue, green, and red light sensors respectively. As you can see from their corresponding wavelength ranges, the sensor's photocurrent response will increase at varying rates based on the given light source's illuminance level, light intensity, and the spectral wavelength emitted along with the peak sensitivity wavelength of the sensor. This is a summary of the D1 blue sensor collected results. As you can see, it gives consistent, distinct results reacting to the blue LED versus the green or red, as would be desired. These are the test results for Q3, our leading green sensor. And these are our results for Q1, which will be used as our red light sensing and /determining sensor. Currently, throughout all the sensors tested, the blue LED always measures the largest photocurrent response, regardless of the predicted datasheet response. This is thought to be due to a complex mix of factors such as the LEDs emitting at different light intensities and ambient light sources interfering. The team is currently looking into ways to scale for this blue LED response. I will be continuing testing 4 different all-in-one sensors, which we have recently decided to try out due to the vast design benefits they will offer for our sensor head over the current choices of D1, Q3, and Q1, assuming the predicted trends hold. This is a list of my technical accomplishments I will be focusing on over winter break and the next semester. My teammate, Nicholas Hatzies, will be discussing the printed circuit board progress us electrical engineers have made, including a sensor test PCB and our final prototype PCB.
This is a list of my technical accomplishments this past semester. I worked vigorously on creating printed circuit boards in order to take data with minimal noise. When testing was first being conducted on a breadboard, it was very apparent that there was a significant amount of noise occurring. So I thought, how can I improve this? So the team came up with the brilliant idea of a printed circuit board. It was decided that the board would have 4 sensors for each color, so 12 in total. The sensors would be separated by color and be controlled by a switch. The schematics and PCB files were made on Circuit Maker. However, Circuit Maker did not possess the footprints for sensors D1 and Q2. Therefore, they had to be created. The test PCB was a simple 2-layer board. A top layer and a bottom layer. The bottom layer would act as the ground plane for the board. We then place vias at each node in order to measure the voltage. The vias would act as our test points. Here are the schematics for the prototype PCB. On the left is the LED sensing sheet. This sheet shows all 12 sensors. On the right of the LED sensing sheet is a sheet symbol. The sheet symbol connects the sensors onto another sheet. The sensors are connected into the multiplexers, which are shown on the right. There are 3 multiplexers, one for each colored sensor. There is also a temperature sensor in order to reduce the risk of overheating. The power for this PCB will be fed through a DC power jack and into a DC to DC converter. 3.3 volts will come out of the DC to DC converter and power on the microcontroller. The microcontroller decided on by the team is from the PIC family. The multiplexers will be fed into the analog inputs of the microcontroller. The prototype PCB will consist of at least 4 layers: a top layer, a ground layer, a 5-volt layer, and a bottom layer. The sensor head will be placed on the top layer, and the components will be placed on the bottom layer. The next steps are for the microcontroller to be placed on the PCB, and for our sensor choices to be finalized pending the completion of the data from the all-in-one sensor. After these steps are completed, the routing can be done and the board can be produced. Once produced, the implementation of firmware will be conducted. My teammate, Toby Awolaya, will be discussing progress the computer engineers have made.
This semester, the computer engineers were tasked with algorithm development, system communication, and user interface design. Displayed on the screen are my key technical contributions. The algorithms were split up into 4 main categories: the ambient light detection algorithm, the blink sequence detection algorithm, the light intensity algorithm, and the color detection algorithm. Over the semester, I carried out several research on topics like spectroscopy to better understand how colors are detected, and I used the information to come up with an algorithm for color detection. As shown in the flowchart above, the LED sensor array sends the data containing information about the peak intensity of the LEDs that shine upon it. Then the data received from each sensor will be summed up to form a ratio. This new sum will be compared to the values we calculated during the sensory characterization stage, and if we find that the sum is similar to the expected value of either the red, the green, or the blue LEDs, then we output to the user and let them know that the red light is on, or the blue light is on, or the green light is on. The process keeps on going until the user decides to stop it. I was also tasked with the overall system communication. Our technical directors gave us the options of using a controller area network or serial method of communication. After research, we decided serial would be efficient enough for our project. We made use of an Arduino and a serial USB-B to facilitate a serial connection to send information to the user interface. We wrote a program on the Arduino that sent a series of made-up data from the Arduino to the user interface. Since we will be sending a lot of data from our microcontroller to our user interface, we decided to make use of PODI's command line interface as a debugging tool. This is a list of what I plan to accomplish the next semester. My fellow computer engineer, John Mendez, will give you more information about how we implemented the serial port on our user interface.
These are the following areas where I have provided key technical contributions. Originally, the COM port settings were hard-coded in Visual Studios using the WinForm serial communication library. In order to grant the user a level of customization, 2 features were added where the user could specify the designated COM port settings. Once specified, the user can establish the communication connection between the PC and microcontroller. Once the connection has been established, the user has the option to either read the data incoming from the microcontroller or send commands to the microcontroller, which would be implemented in the future. Although an Arduino microcontroller will not be used in the final product, it served as a temporary tool in aiding debugging. This is the workflow diagram for the LED on and off algorithm. It starts by taking a baseline of the surrounding lighting. Next, the algorithm will receive the information from the 2x3 LED sensing array responding to the LED it is viewing. Afterwards, the algorithm will normalize the received information. The result will then be compared to the on and off thresholds and determine the LED state. When the team began testing several sensors on a breadboard, it was discovered that it was difficult keeping the LEDs steady as well as the fixed distance in order to collect consistent measurements. Light intensity is defined as the rate of photons that is sensed by the photoelectric devices. Therefore, any slight changes in the distance or the angle of which the LED was aimed towards the sensor drastically impacted the light intensity sensed by the sensor, which would be reflected in our measurements. For testing, the team developed the mounts using two different materials, black filament and clear resin. These are my remaining technical accomplishments before April 15, 2022. I will now go over the future team accomplishments. Once the team has selected the optimal combination of sensors to meet our anticipated best outcome, the team will work together to develop a method in reducing noise. Noise filtering will enable the device to read and deliver concise information as well as be an important implementation that will aid in the development of various algorithms. The team will then work towards completing the prototype PCB and the hardware associated with the sensor head. Once all this is completed, the team will compile a bill of materials alongside a user manual of the system. Our team would like to thank everyone that has helped us throughout the project. Our technical directors Camilo Geraldo, Nate Roth, as well as our consulting technical director Mike Smith. Lastly, we would like to thank our Capstone Program Director, Dr. Harish Sunak, for giving each designer the opportunity to demonstrate their skills in a real-world environment.